In this unit, we're going to begin exploring the implications of organic molecules existing in 3 dimensions and the spatial properties and relationships of organic compounds. This is an area known as stereochemistry. Basically, the study of the spatial properties of compounds is stereochemistry. And really 2 big themes we're going to see throughout this unit are the notion of chirality and stereoisomerism. Chirality is the idea that a molecule can be handed. This is a concept that you have a sense of already from everyday life. We're going to see how it applies in a molecular context and how some of the intuitive ideas you have about handed objects like scissors and screws apply in the molecular world as well. And then there's this concept of stereoisomerism, which is a relationship between 2 compounds that differ only in their spatial properties. There are 2 types of stereoisomerism that we're going to dig into, and we're going to learn how to recognize stereoisomeric relationships and talk a little bit about the implications of different stereoisomeric relationships. What does 2 molecules being enantiomers tell us about the properties of those compounds, for example, is a question that we'll explore on some level in this unit. So the overarching learning objectives, number 1 is define and recognize isomeric relationships between 2 organic compounds. So we're already familiar with the idea of constitutional isomerism, 2 compounds with the same molecular formula but different connectivity or constitution. In this unit, we're going to dig into compounds that have the same connectivity in 2 dimensions, but different positions of groups in 3 dimensions, stereoisomers, and we're going to develop sort of a unifying framework for thinking about isomerism that incorporates both connectivity and spatial positions, or what we'll call configuration. We'll also learn how to recognize whether a compound is handed or chiral or not, and compounds that are not handed are known as achiral. We'll explore symmetry in the molecular structures of organic compounds, particularly reflection and rotational symmetry. Reflectional symmetry is typical of achiral compounds, and rotational symmetry is interesting. It has actually spectroscopic implications that we'll explore later in the course, but is actually not directly related to chirality or achirality, and we'll see that a little bit later. We're going to learn how to label configurations. One thing we'll notice in looking at stereoisomers is that with respect to the naming conventions we've already seen, stereoisomers have the same names. We actually need new naming conventions to distinguish between different stereoisomers, and this is where the RS and EZ here in Learning Objective 9 conventions come into play. These conventions provide us with a means to distinguish between stereoisomers in their names, talking about R&S configurations at what we'll call tetrahedral stereocenters, sometimes known as chiral carbons or chirality centers, and then EZ are used to label stereogenic alkenes. Cis and trans are sort of analogous to these Z and E labels, but the ZE system provides a more general framework for thinking about cis and trans. We'll talk a little bit about the physical properties of enantiomers in particular, looking at this fascinating phenomenon of optical activity. We'll also learn about a convention for drawing 3-dimensional carbon known as a Fischer projection. A bit of an old school convention, but one that's commonly still used in carbohydrate chemistry. We'll look at how conformation and chirality interact, which is an interesting area that we won't explore in too much detail, but we're going to develop some general ideas about how conformation relates to chirality. For example, in cyclohexanes, where the chair flip can change a little bit how we think about chirality in the 2 different chair forms. We'll recognize chirality in compounds lacking a tetrahedral stereocenter, and then we already mentioned this EZ convention for stereogenic alkenes that we'll see at the end of this unit. In this first video, we're going to get kind of a general overview of important stereochemical concepts, and later in the unit, we'll get into the weeds on really applying these concepts to specific organic compounds. And this first slide deals with the concept of isomerism. Isomers are the same in some ways and different in others. They're compounds, for example, with the same molecular formula, but differences in structure. And the nature of the difference in structure is embedded in these adjectives that we put before the word isomer in the various types of isomers. We can think about classifying isomers using sort of 3 levels of organic structure that I like to call the 3 C's. Connectivity, or the old school term is constitution, configuration, and conformation. So we can talk about constitutional isomers, configurational isomers, or what we'll call stereoisomers, and conformational isomers. Constitutional isomers differ at this level of connectivity, and compounds that differ in connectivity have vastly different chemical and physical properties as a result of this difference in connectivity. A bit more similar to each other are compounds that have the same connectivity, but differences in the positions of their atoms in three-dimensional space. These are known as configurational isomers, or what we'll more commonly call stereoisomers. And an example of stereoisomers are these cis and trans dimethyl cyclohexanes, where they're both 1,2-dimethyl cyclohexanes, but they differ in the spatial positions of atoms in three-dimensional space, and this is embedded in the terms cis and trans. As an example of constitutional isomers, we have something like ethanol versus methoxymethane or dimethyl ether, and these are vastly different in their physical properties. Dimethyl ether is a gas at room temperature, ethanol a liquid at room temperature, for example. Conformational isomers are even more similar than configurational isomers and quite frequently rapidly interconvert at room temperature. A good example of conformational isomers would be the two chair forms of a monosubstituted cyclohexane, like this. The equatorial and axial conformations are conformational isomers, and we won't deal with conformational isomers very much in this course, but just to sort of give an overarching framework for isomerism, I think it's important to keep in mind that conformational isomerism is a type of isomerism that we can recognize and think about, and it's that sort of finest level of organic structure. We don't always have to think about it. Quite frequently we can ignore it, but sometimes it does matter. Stereoisomerism is a relationship between two or more compounds. We're also interested in a spatial property of a single molecule or single compound known as chirality. Now, chirality is kind of the fancy term for this, but the term from everyday life, which is exactly equivalent to the term chiral or chirality, is handed or handedness. Objects that are different from their mirror images are what we call handed. And the mirror image is made through the operation of reflection, projecting the image of the molecule, or more generally the object, through a plane and out the other side at an equal distance. So, for example here, we can start by recognizing that many objects in everyday life are identical to their mirror images. For example, this pair of sunglasses looks exactly the same in the mirror as it does in real life. Looking at yourself in a mirror, presuming perfect symmetry for your body, your image is identical in the mirror to your actual image in everyday life. Molecules are quite frequently identical to their mirror images like this, and we use this term superimposable to very carefully describe what we mean by identical. Superimposable means we can line up all of the atoms of the molecule and its mirror image exactly on each other without any differences of the positions of atoms or bonds in three-dimensional space. Here's ethyl chloride, an example of a molecule that is identical to its mirror image. And we can see this if we reflect this molecule through a mirror. So the blue drawing here is meant to evoke a mirror perpendicular to the screen. Reflecting this image through that mirror would produce this mirror image. And this mirror image is identical to the original structure. If you imagine mentally sliding this image over onto the original structure, you'll see that we can line up all of the atoms exactly. And so this is an example of a compound or a molecule that is identical to its mirror image. We call these achiral. They lack this property of being handed. There are not two distinct hands of ethyl chloride. There's just the one hand of ethyl chloride, which is identical to its mirror image, we might say. The one type of molecule of ethyl chloride, its mirror image is the same as the compound itself. Now, there are many objects from everyday life and many compounds in organic chemistry that are not identical to their mirror image, and we call these chiral or handed. A classic example of a handed object from everyday life is a screw. We have right-handed screws with the threads running helically in a certain direction, and we have left-handed screws with the threads running in the opposite direction. And we know from screwing these in, right, that they are very different. They're not identical. They're not perfectly superimposable on one another. And the way we engage with right-handed and left-handed screws, for example, to screw them into a block of wood, is very different. The sense of rotation as we screw those screws in is different. Molecules can be handed as well, and handed molecules are not the same as their mirror images. A great example of a handed molecule is a tetrahedral carbon with 4 different groups attached, and the 4 different colors here are meant to evoke the idea of 4 different atoms or groups connected to that tetrahedral carbon in black in the center. And here's an example of a molecule with actual groups on it that are colored to evoke that same idea. So we have a hydroxyl, H, methyl group, and ethyl group, 4 different groups attached to this tetrahedral carbon at the center. Reflecting this molecule through a mirror plane, or looking at the molecule in a mirror, produces an image that is not the same as the original. So we might call the original molecule right-handed, say it's got this blue group on the right, and the mirror image left-handed. These 2 hands of a chiral molecule are known as enantiomers, and this is one of the 2 types of stereoisomeric relationships that we'll explore in detail in this unit. I wanted to stop here and show you models, 3-dimensional models of 2-handed molecules with tetrahedral carbon linked to 2 different groups as well to really drive this point home. So we have this molecule here, and if we imagine reflecting through a mirror plane that is perpendicular to the screen, pointed directly out towards you, but the mirror, right, is facing the molecule like this, the mirror image is going to look like this. Now, the key thing at this point is to verify that these are not actually the same. They're not perfectly superimposable. So what we want to try to do here is basically line everything up, right? Put the white ball on top of the white ball, red on top of red, blue on top of blue, and black on top of black, with the central tetrahedral carbons overlapping perfectly. If we try to first line up the white balls and move things sort of into place so that things are overlapping like this, we'll notice that although the white and black balls are lining up nicely, the red and blue balls are not lining up. They're not lining up, so these are not perfectly superimposable. If we try to line up those red and blue balls, we'll actually run into the same problem with the black and white balls now not lining up. So if I sort of change how I'm holding these briefly, we can see that now the white and black balls are not lining up in these 2 structures. So they're not perfectly superimposable. There is no way to get these structures to overlap perfectly with all their atoms and bonds in the exact same places. Therefore, they're different, and they are what we call enantiomers. Non-identical mirror images are known as enantiomers. The compounds or the molecules individually we call chiral or handed, and one way we can think about them with deep analogy to everyday life is one is right-handed and one is left-handed. One thing we're very interested in explorations of stereochemistry is recognizing whether a molecule or compound with given molecular structure is chiral or not. And a structural tool, a concept that's very useful for exploring chirality and stereoisomerism, is known as the stereocenter. It's also called a stereogenic center, asymmetric center, or chirality center. And you'll hear me refer to tetrahedral stereocenters specifically as these carbons with 4 different groups attached to them. So the classic example of the stereocenter has this general structural pattern here, with a carbon connected to 4 different groups, A, B, C, and D. And in fact, the model we were looking at earlier has this structural pattern embedded within it. Say A, B, C, and D. That's 4 different groups attached to a tetrahedral carbon. And you'll quite frequently see wedges and dashes drawn at tetrahedral stereocenters to specify where these groups coming out of the planar screen and going back into the planar screen are actually located. Now, to be a little more precise, a stereocenter is an atom where the exchange of 2 groups, and it's often easiest to do this with the wedged and dashed groups at a stereogenic tetrahedral carbon, produces a compound that is not the same as the original structure, specifically a stereoisomer of the original structure. And I want to show you what this looks like with a carbon connected to 4 different groups. to really drive home what we mean by stereocenter. But this concept of exchanging two groups and seeing what happens to the structure also works for what we'll call stereogenic alkenes. We're going to explore those later in the unit when we return to this idea of cis and trans isomers not being the same and being diastereomeric. But let's dig into what the stereocenter means at a tetrahedral carbon linked to 4 different groups. One thing that I want to return to with these models is, again, reiterating that these are not the same. The 2 mirror images we generated are not the same. But if I exchange 2 of the groups, for example, if I exchange the black and white groups at this carbon, which I'm going to do, we'll notice that something interesting happens here. The exchange of 2 groups has now made this structure where we exchanged identical to that original mirror image. That exchange of 2 groups has turned this molecule into its enantiomer. These are identical, and this is probably the easiest way to see this. We could get everything in these 2 compounds to line up perfectly, these 2 structures to line up perfectly. So exchanging 2 groups converted this molecule into its enantiomer. And in the middle of this slide, we see 3 examples of compounds with a carbon like this, highlighted in green, where exchanging the wedged and dashed groups produces the enantiomer of the compound. For example, here, if we exchange the hydrogen and chlorine, we move the hydrogen where the chlorine is located and the chlorine where the hydrogen is located, the resulting structure would look like this. And you should definitely verify this is not the same as the original structure. Logically speaking, this carbon fits this general structural pattern of 4 different groups, methyl, ethyl, H, and Cl, attached to a central tetrahedral carbon. And so exchanging 2 of those groups, just like we saw for the models, is going to lead to the enantiomer of that structure at the top. Because these are not the same, that carbon highlighted in green, the carbon bearing the bonds that we exchanged, is a stereocenter. Likewise for these other 2 examples, and these are good to try on your own. Try exchanging, for example, the hydroxyl group with the implied dashed hydrogen and seeing what happens to the structure, and try doing the same thing with this bromine and the implied dashed hydrogen of that stereogenic carbon as well. I mentioned earlier that at tetrahedral stereocenters, you'll commonly see wedges and dashes. However, in some representations, you actually won't. For example, in a mixture of the 2 enantiomers, or in an achiral compound, you may not actually see wedges and dashes, even though the compound contains stereocenters. And so to practice building this skill of recognizing where stereochemistry is relevant in a molecule, we're going to locate the tetrahedral stereocenters in this kind of flat-looking structure of vitamin D3. So the structure looks flat with no wedges and dashes, but we got to keep in mind that there are a number of tetrahedral carbons in this thing, and so in reality, groups are existing in 3 dimensions. There are some groups that are going to be coming out of the plane of the screen, some groups going back into the plane of the screen, that kind of thing. And in looking for a tetrahedral stereocenter, what we're looking for are these carbons with 4 different groups linked to them and the tetrahedral geometry. So take a minute. I'm actually going to take a sip of coffee, and I want you to try this on your own. Try identifying the tetrahedral stereocenters in vitamin D3. You're looking for carbons with 4 different groups linked to them. All right, let's dig in and see what we can find here. So one thing I want to point out first is some tempting carbons that are not actually stereocenters. This carbon right here, not a stereocenter. It may look nominally like it's got 4 different groups attached to it. There is an implied hydrogen here. But the 2 methyl groups are identical. The 2 methyl groups attached to this carbon here, these are the same. And so this is not a carbon with 4 different groups attached to it. It's not a stereocenter. The isopropyl group, which is this entire group here, is not stereogenic. All right, the first carbon that jumps out at me, and where you see a large number of bonds, the mental alarm bell should kind of start going off. If you see 3 or even 4 bonds drawn explicitly, you should start looking for the potential for a stereocenter there. The first carbon that jumps out at me that's like that is this one with an implied hydrogen and 3 bonds drawn explicitly here. And we have 4 different groups. We have this carbon chain, we have the methyl group, we have this methine carbon and everything that's attached to it, and we have the hydrogen. 4 different groups. That is a stereocenter. Now, we don't know how atoms are arranged in 3-dimensional space around this stereocenter. We need wedges and dashes to find that information. But what we can still say here is that that carbon is a stereocenter. Okay, next carbon that jumps out at me is this one right here. 4 bonds drawn explicitly, but let's verify that the 4 groups attached to it are actually different. We have a methyl group here. We have a CH2 group here, so those are clearly different from each other. We have a methine here, a CH with 2 other carbon groups attached to it, and we have a methine here. And these 2 carbons are not the same, right? The overarching groups are not the same. This carbon is linked to this whole chain here. This carbon is linked to a completely different chain. So those 2 groups are different from each other. We're looking at the groups as a whole. If there's any difference between those groups that the carbon is attached to, we consider them different. So we do indeed have 4 different groups attached to this carbon, and that is a stereogenic center or a stereocenter. All right, there's one more tetrahedral stereocenter here, and again, I'm looking at carbons where I've got a number of different bonds explicitly shown. 3 or 4 bonds explicitly shown is often a dead giveaway for a stereocenter. And here again, I think it's helpful to draw in the implied hydrogen. And what we can see here is we do indeed have 4 different groups. I have an H and an OH, clearly different from each other. I have a CH2 that's connected to an alkene here, and a CH2 that's connected to another CH2 here. So these 2 groups are in fact different, and so we are dealing with a stereocenter right here as well. So 3 tetrahedral stereocenters in vitamin D3, and again, in this representation, we don't have any information about where the groups are actually located in 3-dimensional space. We need wedges and dashes in the structure to actually have that information. Finally, let's return to this notion of enantiomers. Enantiomers have a special type of stereoisomeric relationship. They have all the same connectivity, same molecular formula, they just differ in the positions of atoms in 3-dimensional space. And enantiomers are particularly special because they are mirror images. And this makes them, as I like to call it, as similar as 2 molecules can possibly be without being the same. They have all the same bond lengths, all the same internal distances between different functional groups and that kind of thing. And this leads to identical physical properties, with one important exception that we'll explore a little bit later. Enantiomers are extremely, extremely similar. They differ in how they interact with other chiral compounds and chiral phenomena, which turns out to be really important in a biochemical context. But they're very, very similar. And the first example of enantiomers I wanted to point out is one we've already seen, this example of tetrahedral carbon bound to 4 different groups. This generalizes regardless of the complexity of the groups. So you could imagine extremely complex structures at each of these balls. These 2 molecules would still be enantiomers, assuming there weren't any additional stereocenters differing in configuration inside the balls. But assuming all of these groups are individually achiral, these 2 molecules are enantiomers regardless of the nature of those groups. They're mirror images, but as we noted earlier, they are not the same. They're not perfectly superimposable. And enantiomerism and chirality tends to appear when we have a tetrahedral stereocenter, a carbon connected to 4 different groups. The slide makes this point, and these 2 models make the point, that a chiral compound has one and only one enantiomer. There is one and only one mirror image of this molecule, and it's this molecule, and that is the enantiomer of this. The mirror image of this, well, that's this molecule, right? And so just like there are only 2 possible hands for a given shape of a particular hand, right? There's a right hand and a left hand, and that's it. There are only 2 molecules in an enantiomeric pair, and a given molecular compound has one and only one enantiomer, the mirror image of that compound. So finally, let's practice with enantiomerism by drawing the enantiomer of ketamine, which is a chiral anesthetic. Now, the first thing we should do, and it's worth pausing the video and doing this, is looking for a tetrahedral stereocenter. Look for a carbon with 4 different groups attached. See if you can find it in the structure of ketamine. Did you find it? Well, there's a carbon with wedges and dashes in the structure, right? There's a carbon with 3-dimensional information right there, and this is indeed a stereocenter. I've got a nitrogen group here, I've got a benzene ring here, I've got a carbonyl group here, and I've got a CH2 group here. 4 different groups attached. This suggests that the molecule is chiral. We've got a tetrahedral carbon with 4 different achiral groups. Each of these groups is pretty much flat. Any 3-dimensionality is equivalent above and below the plane of the screen. And so we've likely got a chiral molecule here. And we can verify that by drawing the mirror image and comparing it to the original structure. Now, how you draw a mirror image is actually really important to understand. And I'm probably going to link out to a video where I talk in more detail about the topological operation of reflection in a little more detail. I won't belabor the point here. I'll just say that reflection corresponds to projecting each atom through the mirror plane and out the other side at an equal distance. So this is not a rotation. It is not a flipping of the molecule, which of course wouldn't change the configuration, wouldn't change the relative positions of any of the groups in 3-dimensional space at all. This is an actual projection of the atom through a plane. For example, this nitrogen is going to remain above the plane when it's reflected through this mirror that is perpendicular to the screen. And this benzene ring is going to remain below the plane upon this reflection. And this 6-membered ring is going to remain in the plane after this reflection. And so I'm going to go ahead and lay down the mirror image here, and we're going to note how this was actually generated. So for example, to reflect this benzene ring, what I did was I said, okay, closest to the mirror is this carbon. And so this carbon appears closest to the mirror. Farthest from the mirror is the chlorine. And so that's going to appear relatively far from the mirror in the mirror image. And likewise for the other atoms involved. This nitrogen, relatively close to the mirror. And so it's going to be relatively close to the mirror in the mirror image, and likewise. And so if need be, pause the video and make sure you can verify how this reflection was done. And if you need to, check out the linked video on the topology of reflection as well. Now, the last thing we need to do here is verify that these are actually not the same. We don't necessarily need to do that, given that the problem mentions, hey, this compound is chiral, but in fact, these are not the same. We've got 4 different groups attached to a tetrahedral stereocenter in different ways, and that operation of reflection pretty much has converted one enantiomer into the other enantiomer, and these are not the same. So for example, in this view, at least to my eye, this white group looks like the NH2 group, right, pointed out towards you. The red and black groups look like groups in the 6-membered ring, with the black group being the carbonyl and the red group being the CH2 on top. And then, wait a minute. There we go. So now we have the NH2 groups pointed out towards you. We have the red groups are the CH2s in the 2 mirror images. We have the black groups at the bottom are the carbonyl groups in each enantiomer, and we have the blue groups are the benzene rings. So notice this very simple model, taking out the complexity of all the junk built into those groups, is helpful for convincing us that these 2 enantiomers are not the same compound, that the operation of reflection has actually converted the original molecule into a completely different structure.